So, st- hello. So, uh, why it is not?
Do you have any problem? The screen is showing for us.
Yeah. Okay. Nice. So, good afternoon, everyone. I am Riju Pal. Currently, I am a postdoctoral researcher at IFW Dresden, Germany. So, I did my PhD at Bose National Center for Basic Sciences, Kolkata, India. So, the title of my presentation is Emergent Phases, Unconventional Magnetotransport and Magnetic Anisotropy in a Quasi-2D Ferromagnet, Iron 4, Germanium Telluride 2. So part of this work is done during my PhD, and part of the work I did at IFW Dresden during my PhD tenure. So before going to the details of the current topics, I would briefly introduce the field of my research. So we all know that, yeah. So we all know that the field of 2D materials got emerged after the discovery of graphene, which is a one atomic thick layer from which can be exfoliated from the bulk graphite crystal, because in the bulk graphite phase, the layers are contacted with like van der Waal interaction, weak van der Waal interaction. So after the discovery of graphene, a lot of 2D materials were synthesized. They are in different forms like insulator, semiconductor, half metal, semi-metal, metal, superconductor, etc. But there is a missing member in this family till 2016 called 2D magnet. And it was explained by Marmin and Wagner that thermal fluctuation destroy the long-range magnetic order in 2D system at any finite temperature. But first experimental breakthrough happens in 2017 when two experimental groups synthesized two materials, that is, one is chromium iodide and another is chromium germanium telluride. In both cases, they have shown that the materials are ferromagnetic and they can be stabilized down to the monolayer limit, and they can persist even at finite temperature. So, in both cases, magnetic anisotropy plays a key role for the stabilizations of the long-range magnetic order down to the monolayer limit at finite temperature. So, after that, a lot of 2D magnetic materials were synthesized. They have different applications, like they have shown magnetic tunnel junctions based device performance, spin orbit torque devices, distance magnon transport is possible. So in all cases, like the main disadvantages of these crystals are that their ordering temperature is much lower than the room temperature. Also, they are much air sensitive. So the practical applications was lacking so far. So the main point is that we have to have the higher ordering temperature and with less environmental sensitivity. So here the strategy was taken that we can see that this is the ordering temperature of this magnetic materials in 2D limit, that is depends on the spin exchange interaction as well as the magnetic anisotropy. So the main motto was to enhance the magnetic spin exchange interaction while keeping this magnetocrystalline anisotropy smaller. Later this iron based family, iron germanium telluride, came into play, and here we can see that a stronger exchange interaction, and if we increase the iron concentration, basically that will increase the exchange interaction, and thus we will be getting the higher ordering temperature. So our interesting focus on the material system is that iron 4 germanium telluride 2 having nearly room temperature ferromagnetic order. It has a higher conductivity, large magnetization, also smaller magnetic anisotropy with high Tc. And most interestingly, it has a spin reorientation transition near 110 Kelvin. That means if we see about the magnetization curve, then if we decrease the temperature, then the magnetic easy axis lies in the AB plane in the higher temperature. But if we go to the below 110 Kelvin, then the magnetic easy axis lies along the C axis. So there is a change of the magnetic easy axis with temperature. So we basically focused on this material. So it has a rhombohedral crystal structure and 7 atom creates a monolayer of it. So also there it was reported that if we decrease the thickness of the layer, then its spin reorientation transition can be shifted towards the room temperature. So there is a unique interplay of this spin orientation part, and also we can easily tune this material system in various aspects. So our goal was to investigate the spin orientation transition through magnetotransport measurements and to investigate the origin of the anomalous Hall effect in this compound by Hall measurement. And also we have focused on the magnetic anisotropy of the system and spin dynamics through ESR measurement. So first I will focus on the transport part. So we have taken our bulk crystal and we have exfoliated this material and we have transferred this flakes on top of a pre-patterned gold electrodes and we have measured our crystal with normal 6 probe geometry. So if we initially see the resistivity curve, then we can see that if we decrease the temperature, the resistivity shows a metallic behavior and its metallicity got enhanced if we reduce the temperature below 150 Kelvin. And so if we derivative the resistivity curve, which is shown is as the red dotted line, so we can see a kink around 120 Kelvin, which is close to the spin orientation transition. Also near the magnetic transition, we have not seen a significant change, but we have seen a significant change near 40 Kelvin, which I will explain its consequences. But before that, I would like to focus on the scattering mechanism in this compound. So we know that for metallic ferromagnet, the total resistivity is the sum of the impurity scattering, electron-electron scattering, electron-phonon scattering, and for magnetic materials, it is electron-magnon scattering. So from the temperature dependencies, we can see that it varies like this in different terms. So we have tried to fit our data. So where in the higher temperature regime, we have seen that electron-phonon scattering is the dominant scattering mechanism here, but in the intermediate temperature range, T plus T square is responsible, and in the lowest temperature part T square is responsible. So from this equation we can see that electron and electron magnon both depends on T square. So to disentangle that which part is corresponds to this T square behavior in these two regions, we have performed a magnetic field dependence. So we have you can see that these blue and green curves are the magnetic field 9 Tesla magnetic field dependence for both in plane and out of plane. This is the resistivity and this is the temperature dependence of resistivity. And we can see that up to this particular temperature around 40 Kelvin, there is almost in non-sensitive, insensitive behavior with the magnetic field that corresponds to the electron-electron scattering mechanism in this low temperature part, which provides the Fermi liquid behavior here. But in the intermediate temperature range, we can see a strong magnetic field dependence, which corresponds to the dominant scattering mechanism electron magnet here. And then the T is the electron phonon scattering mechanism here. So after that, we have focused on the magnetoresistance part, and this is the temperature dependence of magnetoresistance, where at the low temperature it follows the positive magnetoresistance, but if we increase the temperature, then at the higher temperature we can see negative magnetoresistance, and there is a definite crossover near this TQ, that is around 40 to 50 Kelvin, and we can get that is the maximum negative magnetoresistance we are getting near the spin orientation transition. Then we have focused on the Hall data, and we know that the Hall resistivity for a ferromagnet is sum of the ordinary Hall effect plus anomalous Hall effect. So to separate it out, the ordinary and Hall coefficient, we have used our methods, and we can found that the ordinary Hall coefficient changes sign at different temperatures. Like at the intermediate temperature regime, we can see that it shows like a majority carrier as a electron, but if we go below 50 Kelvin and above 150 Kelvin, we can see majority carrier charge carrier becomes hole. So there is a definite change of the type of charge carrier here. And also we have seen that from the anomalous Hall effect, that maximum anomalous Hall coefficient and maximum anomalous Hall conductivity near the spin orientation transition. Also, we have seen that there is a definite temperature dependencies of the anomalous Hall conductivity, and we from our analysis we have found that the side jump scattering mechanism is responsible for this anomalous Hall effect. So, later to investigate about the spin dynamics of the system, we have performed electron spin resonance spectroscopic study here. So briefly, we can tell that I can tell that this spin orientation, this electron spin resonance is a spectroscopic tool which mainly focuses on the spins of the electron. So let's say if we have a spin half of the system, then if we apply an external magnetic field, then its spin states will be splitted with the energy difference like this. And if we apply a microwave radiation, then if there is a resonance field and resonance frequency, then in the paramagnetic state, we can get the resonance conditions like this. And in the resonance condition, microwave is getting absorbed by the spin half system. And we can see the resonance field from this spectra, from the minimum of the spectra. So this is a very much important tool for investigations of the magnetic anisotropy of the system, the determination of magnetic easy axis, magnon excitations, gas, spin-spin correlations, spin dynamics, etc. Now, if we have a ferromagnetic system, then we have to excite the net magnetization of the system, and the full things will be followed by the Landau-Lipschitz equation. And here, if the system has an anisotropy, then the anisotropy will be given by the anisotropy field, that is HA. And this HA will shift the line from the position given by the G factor. And after using this, we can get the analytical expression for spin wave energies for uniaxial ferromagnet like this. So after that, we focused on this experiment, and you can see that if we apply an external magnetic field out of plane direction, and if you apply a fixed frequency around 90 gigahertz, then at 3 Kelvin, we can see this is the resonance spectra, and this black line is the expected paramagnetic line. So at 3 Kelvin, you can see that there is a definite shift of the line. That means there is an anisotropy of the system. And if we increase the temperature, then we can see that the line shifts towards right, it crosses at certain temperature and the paramagnetic line, and it goes towards right, and again at higher temperature it goes to the paramagnetic line. In the in-plane orientation, the situation is opposite, but more or less similar, that it's started from right, goes crosses at certain temperature, goes to the left, and again moves towards the expected paramagnetic line. So if we extract the resonance fields, then we can see that the temperature dependence shows that there is a crossover of the expected paramagnetic line. That means near this 110 Kelvin, that is spin orientation transition, there is a change of the type of anisotropy in both cases. And also near this 300 Kelvin also, we can see that the resonance line does not reach to the paramagnetic line. We know, we have seen that the ordering temperature is 270 Kelvin. So around 30 Kelvin above, we can not see the
Sorry, you have 1 minute left.
Okay.
1 minute.
Yeah. So after that, we focused on the frequency dependence part, and we can see we have tried to fit the spin wave energy expression at different temperatures, and we can see that at 3 Kelvin and 110 Kelvin, it shows easy axis ferromagnet and isotropic behavior. But around 200 Kelvin, we can say that the data is well fitted with easy plane ferromagnetic equation. And after that, we have investigated our results and plotted with respect to the temperature, the total anisotropy field. And we know the total anisotropy field is the sum of the magnetocrystalline anisotropy plus shape anisotropy. So the shape anisotropy you have calculated from the magnetization data is plotted with this blue data point, a green line. And if we extract the intrinsic magnetocrystalline anisotropy, we can see that this flows like this star. And interestingly, we have found that the magnetic easy axis is fully the system is fully magnetic easy axis here, and the competition between magnetocrystalline anisotropy and shape anisotropy behaves isotropic behavior near this 110 Kelvin. So finally, I would like to conclude here. So we have seen different inelastic scattering mechanism at different temperatures. We have seen identified a new electronic transition. We have seen maximum negative magnetoresistance near the spin orientation, and also ESR study shows the quantitative insights into the non-trivial temperature evolutions of magnetic anisotropy. And interestingly, we can see that all the transport results and ESR results match that temperature points. That indicates that there is inherent coupling between electronic and magnetic degrees of freedom. So you can find the results in these two publications. And finally, I would like to acknowledge my PhD supervisor, Dr. Atindranath Pal, Professor Prabhat Mondal for crystal synthesis supervision, my lab mates, Professor Tanushi Gupta and Professor Dr. Bernd Buchner for this collaborative work at Germany, Professor Dr. Bernd Buchner, Dr. Kataev, Dr. Alfonso for helping me the ESR measurement. And finally, I'd like to acknowledge IEEE and AtC-AtG for providing me the opportunity to present the work here. Thank you so much.